In this video, I'm going to teach you how to sum the forces. The first step is to identify the positive and negative direction. You've seen these equations repeatedly, which are essentially stating that the sum of forces, or net force, is equal to the summation of all the forces acting in a given direction. What I like to do is identify my negative forces and subtract those from the positive forces. Let's look at an example at which an object is at rest on a table. Of course, we'll start with our free body diagram where we have the upward force of the table on the object and the downward force of the earth on the object. Let's call up positive and down negative, and then when we sum the forces and set those equal to mass times acceleration, we can solve this expression. Notice how I'm using an additional subscript to denote that we're looking at the summation of the forces vertically or in the y direction and the acceleration of the object in the y direction. Also note that this object is not accelerating in the y direction, which means the right side of this expression becomes 0. And if we add the force of gravity to both sides, we can then show that force normal is equal in magnitude but opposite in direction to the force of gravity. Okay, here we have a man applying a force to an object on a rough surface, and the object accelerates. That's important. Rough implying there is friction, and acceleration applying that there's these unbalanced forces acting in the horizontal direction. Let's start with our free body diagram. Again, we have force normal, force of gravity, and this time we have two forces acting in the x or horizontal. We have the rightward force applied, and we have the leftward force of friction. Notice how force applied is drawn greater in length relative to the force of friction because we are explicitly told this object accelerates to the right. We'll call right our positive and left our negative. We'll do our summation now in the horizontal or x direction. Notice how I am taking my negative force, which is the leftward force, which is the force of friction, and subtracting it from the rightward force, which is the force applied. Let's do the same in the y direction, and you'll see something quite familiar. Because this object is not accelerating in the y direction, once again, we can state that the force normal is equal in magnitude but opposite in direction to the force of gravity. Okay, here I'm pulling an object across a smooth surface. Okay, so I'm pulling it across the smooth surface. Let's analyze this situation starting with your free body diagram. I will underline the word smooth because that implies friction is negligible. So we're going to neglect friction, which means we only have 3 forces in total acting on this object, 2 acting in the y direction and only 1 acting in the x direction. Identifying our positive and negative directions allows us to then sum forces horizontally. Some students get tripped up when they see there's only 1 force in the x direction. That's right, guys, the force of tension. The rightward force of the rope on the object is indeed the only force acting horizontally, which means this object is going to accelerate horizontally in the direction of that force of tension. Now, in the y direction, once again, we see that because there's no acceleration in the y direction, force normal is equal in magnitude, opposite in direction to the force of gravity. But what about when forces are not directly in the x and y directions? This is where we start having fun. You need to then resolve these forces into their components using trigonometry. Let's take a look here at a bocce ball hanging by 2 strings. And I probably have something similar to this set up in the front of the classroom. Okay, now the second bullet here I will address through this example. All right, so if required, you will be doing a total of 2 free body diagrams. One with it unresolved, the forces, and one with the forces resolved into components. Okay, let's call the force of tension T1 and T2. And then let's go ahead and identify our right-angled triangle, which is comprised of the force of T1 in the y direction and the force of T1 in the x direction. And let's do the same thing then for T2, where we can identify the vertical and the horizontal components for these. Now again, guys, T1 and T2 are the hypotenuse of these right-angled triangles, and therefore they are referred to as the resultant vectors that are unresolved. Don't forget the downward force of the earth on the bocce ball, which is in this case acting in the vertical direction straight down toward earth. Let's do a free body diagram, and let's do this one in which the forces are not resolved into their components. So we have three forces acting on this bocce ball, and they are represented on this free body diagram. Notice force of tension 1 is greater in length than force of tension 2, which implies that T1 is greater than T2, which is accurate. And I'll show you that at the end of this video. Now let's do an example in which we do resolve these into their components. Well, in this case here, we have two forces acting horizontally. Again, notice I've drawn the length of those to be the same. I didn't mean to do that. I'll show you that with some upcoming examples. Then we have the downward force of the earth on the bocce ball. And next we have not one, but two upward forces when we resolve these. We have T1 in the y and T2 in the y. So this is an example of a free body diagram in which components, the forces have been resolved into their components. So we have a free body diagram in which there are no components and one in which there are components. The reason I'm making a big deal out of this is on assessments, quizzes, exams, you may be explicitly told to do a free body diagram without components, in which case you would draw a free body diagram as you see the one on the left. However, many times you will need to do both to solve a problem. Okay, let's sum the forces here. Let's start in the y direction. And just as we did in kinematics, remember, we're going to only look at the y direction. Then we will look at the x direction. So let's call up positive and down negative. So summing the forces here and acknowledging this bocce ball has no acceleration, vertical or horizontal for that matter, we can then therefore state that T1 in the y plus T2 in the y must be equal to the force of gravity. Now let's introduce our angles theta 1 and theta 2, as you can see on the schematic here. Let's insert our trigonometry. Let's start with T1. Remember, T1 is the hypotenuse or resultant vector, and we're trying to solve here for the vertical component, which is opposite. So let's use the sine function of the opposite over the hypotenuse. Let's multiply both sides by T1 to say that T1 in the y direction is equal to T1 times sine of theta 1. And of course, you can do the same thing for T2 and plug that into our summation vertical, and that would be as far as we're going to go there. Now, let's go ahead and consider the horizontal direction. Let's call right positive. Let's call left negative. So I'm subtracting my negative force from the positive force. It's not accelerating horizontally, which means if I add T2 and the x to both sides, I can state that the horizontal components of both of these are the same. Let's look at the trigonometry here. In this case here, because we are solving for that side of the right angle triangle, let's use a cosine function. Rearranging this, we can state that the force of tension in the x direction for tension force 1 is equal to tension force 1 cosine theta 1. All right, now we can plug that into our summation for the horizontal, and we'll be done with this problem here. So what about for an object on an incline? Well, for that, we're going to actually be resolving these forces into their perpendicular and parallel components using the exact same process that we've done here. So in this video, I've taught you now how to take your free body diagrams and use them to solve mathematical problems explicitly, really trying to find the acceleration of an object. And I'll see you guys in class.